Okay, let's unpack this. Have you ever wondered how chemists build these incredibly complex molecules like life-saving drugs or advanced materials from simpler components?
Hmm.
So often it starts with something that sounds simple, just swapping out one atom or group on a ring of carbon atoms for another, like customizing a basic building block.
Indeed. And today we're taking a deep dive into one of organic chemistry's most fundamental and really powerful transformations,
Mhm.
aromatic substitution reactions.
Right.
We're drawing our insights directly from, well, a real cornerstone text,
Hmm.
Advanced Organic Chemistry, Part B Reactions and Synthesis, 5th ed. Specifically, there's this illuminating chapter that just lays out the whole toolkit for how we manipulate these incredibly stable aromatic rings.
Okay, so our mission today is to pull out the most important nuggets of knowledge from this pretty dense chapter. We'll explore the major reaction types, the clever strategies chemists use, the underlying mechanisms, and yeah, plenty of concrete examples. We'll define those technical terms in plain language, really emphasizing their practical synthetic applications. Think of it as, a shortcut to being well-informed on a topic that underpins so much of modern chemistry. And maybe we'll surprise you with just how ingenious some of these transformations can be.
And you'll discover how these reactions, some of which, believe it or not, were first uncovered over a century ago,
Wow.
are still being refined and revolutionized by new discoveries. They offer a level of precision and efficiency in chemical synthesis that just wasn't previously imaginable. It's truly a testament to ongoing innovation in a field that, some might mistakenly perceive as old or settled.
Yeah, chemistry's always moving forward.
Absolutely. And these reactions are a perfect example.
Okay, so at its heart, aromatic substitution is about introducing new groups onto an aromatic ring or replacing existing ones. And these rings, like benzene, everyone knows benzene, they're famously stable.
Right, because of that electron delocalization.
Exactly. The electrons aren't stuck, they're spread out over the whole ring like a cloud. It makes them remarkably resistant to a lot of typical reactions. So getting them to react at all and in a controlled way, well, that requires specific, often quite clever approaches to overcome that stability.
You've hit on a crucial point. Historically, these synthetic methods were among the very first to be developed in organic chemistry, maybe even before we fully understood the mechanisms.
Hmm.
Yet they remain indispensable, both in cutting-edge academic research and, large-scale industrial applications today. We categorize these reactions primarily into three broad types based on what's doing the attacking.
Oh.
There's electrophilic aromatic substitution, where an electron-loving species attacks. Then nucleophilic aromatic substitution, where an electron-donating species is the aggressor. And finally, radical aromatic substitution, involving species with unpaired electrons.
Gotcha. Three main flavors.
Exactly. And each type, as you'll see, has its own unique set of conditions, mechanisms, and, well, powerful applications.
One of the most fascinating aspects, for me anyway, is when you already have a group on the ring, how that group dictates where the new group lands. That's regioselectivity, right?
Yes,
Like, you imagine the ring as a clock face, existing group at 12. The new one can go ortho next door, like 11 or 1 o'clock.
Mm-hmm.
Or meta, 2 carbons away, 10 or 2. Or para, directly opposite at 6 o'clock. And controlling that's vital for building specific molecules, getting the right isomer.
To elaborate a bit, envision an aromatic ring, maybe represented by X, with a substituent attached. An incoming electrophile that's an electron-loving species, E plus it can replace an existing hydrogen or sometimes another group.
Okay.
Common electrophiles. Things like the nitronium ion, NO2 plus A for nitration, halogens fluorine, chlorine, bromine, iodine, sulfonic acid, the SO3H, or even carbon groups, alkyl or acyl groups, like or RCO.
Right.
And the electronic nature of that existing X group, it profoundly influences where that E plus attacks.
Yeah.
Some X groups donate electrons, making the ring more reactive.
Activating it.
Activating it, yeah. And they direct attack to the ortho and para positions. Others withdraw electrons, making the ring less reactive.
Deactivating.
Deactivating and directing attack mainly to the meta position. Understanding that interplay is just fundamental to predicting and controlling what product you're going to get.
Okay, so beyond these direct attacks by electrophiles, you mentioned this incredibly versatile class involving aryl diazonium ions, known since the 19th century, you said.
That's right, and still seeing development today.
Yeah.
They're like a special temporary handle you can put on the ring
Oh.
that can then be swapped out for almost anything else. It really expands the possibilities way beyond direct electrophilic or nucleophilic attack.
Precisely.
These diazonium ions, They provide pathways to introduce a huge array of groups that are otherwise really difficult, maybe even impossible to attach directly.
Like what kind of groups?
Well, things like aryl halides, fluorine, chlorine, bromine, iodine, cyanides, CN, azides, N3, phenols, OH, even some alkynyl derivatives. Their power lies in the fact that they essentially act as this handle on the ring that can be cleanly replaced by various nucleophiles.
And a nucleophile is nucleus-loving, electron-rich.
Exactly. Electron donating. It's rich in electrons, looking for a positive center or an electron-poor region to attack and form a new bond. And the key here is the diazonium group itself is a superb leaving group.
What leaves?
Nitrogen gas, N2. Incredibly stable. That's the driving force.
Okay. That makes sense. Now, here's something that often trips people up, I think. Trying to directly displace, say, a halide from an aromatic ring using a nucleophile. Just mixing them together, that's generally really hard, right? It's totally different from reactions on simple saturated carbons where SN2 is common. Aromatic rings just don't play ball that way.
You're absolutely right. Direct SN2-like reactions. They just don't happen on aromatic rings. The geometry, the electron density of those sp2 carbons, the nucleophile can't get in from the back like it needs to for SN2.
Right.
But nucleophilic aromatic substitution can occur through different mechanisms. One is the addition elimination mechanism, often called SNAR. The nucleophile adds first, forms an intermediate.
A Meisenheimer complex.
Exactly, a Meisenheimer complex. Then the leaving group gets eliminated. Another way is elimination addition, which goes through that highly unusual intermediate called benzene.
We'll definitely get to that.
Oh, yeah. But what's truly exciting, and has led to really rapid development, is metal ion catalysis, particularly copper and palladium catalysts.
The modern methods.
These have dramatically improved procedures. They allow displacement of groups like iodine, bromine, chlorine, even sulfonates by nucleophiles like cyanides and amines, alkoxides, things that were very difficult before. They allow it under much milder conditions, too. It's a fundamental shift in our ability to build complex molecules.
And for those who like a bit of a wild card, there are radical reactions, too.
Yes, some useful synthetic applications involve radical reactions, things like direct radical substitution, often used for coupling rings together to make biaryls, and the fascinating SRN1 reaction, which involves electron transfer. We'll unpack those later as well. It just shows the breadth of strategies chemists have developed.
Okay, great. So let's dive deeper into that first category, electrophilic aromatic substitution, or EAS. You mentioned we might remember this from earlier studies.
You might, yeah, if you've had some organic chemistry. Here, though, we're really emphasizing the synthetic methods and their practical applications, how these reactions are actually used in the lab to make specific things, rather than just a theory. Why choose this reagent over that one, you know?
Gotcha. Let's start with nitration then. Nitration, putting nitrogen onto an aromatic ring. You said this is the most important method. Why is it so central?
Well, it's absolutely crucial because nitro compounds, they're easily converted into amino derivatives, usually by simple reduction.
Right, NH2 groups.
Exactly. And those amino groups, as we mentioned, they open the door to forming those incredibly versatile diazonium ions.
Which can then be swapped for almost anything.
Precisely. Halogens, hydroxyls, even just hydrogen. So nitration is this critical gateway. It creates a starting point for a whole world of aromatic transformations.
Okay.
It's also a very general reaction, which is a big plus practically.
Yeah.
You can find good conditions for both highly reactive activated rings
With electron donating groups.
and less reactive deactivated ones, those with electron withdrawing groups. So you have a wide range of substrates you can use.
That's handy.
Plus, here's a neat trick. Each incoming nitro group actually makes the ring less reactive. It has a deactivating effect.
Self-limiting almost?
Kind of, yeah. So it's typically easy to control conditions to get just a single nitro group if that's what you need. Minimizes unwanted multiple nitrations. If you do want more, you just push harder, use more vigorous conditions. That control is a real boon.
Okay. And the classic reagent system is concentrated nitric acid, maybe mixed with sulfuric acid.
Yep, the workhorse combination. The mix with sulfuric acid is generally more reactive, more efficient, indeed. The active species, in both cases, is the nitronium ion, NO2+, a highly reactive electrophile. It's formed by protonating nitric acid, then losing water.
Okay.
Sulfuric acid being a stronger acid than nitric, it just helps generate a much higher concentration of this powerful nitronium ion. Sort of supercharges the nitric acid, makes the reaction faster, more efficient. Nitration can also happen in organic solvents, things like acetic acid or nitromethane. In these cases, Forming the nitronium ion itself is often the slow step, the rate-controlling step.
Right.
What's particularly interesting is dissolving nitric acid in acetic anhydride. That generates acetyl nitrate. And this reagent, it often gives high ortho-dot para ratios.
Oh, interesting. So it changes the regioselectivity compared to mixed acid.
It often does, yeah.
Yeah.
That preference for ortho positions can be really important when you need a specific isomer.
And for convenience, you can generate trifluoroacetyl nitrate in situ. Just mix the ingredients in the flask.
Yep. Exactly. Reacting an aromatic compound, say in chloroform, with a nitrate salt and trifluoroacetic anhydride, avoids handling the preformed, highly reactive nitrating agent. Safer, easier.
Nice.
Even more interesting for selectivity. Using acetic or trifluoroacetic anhydride with nitric acid, but adding zeolite beta catalysts. Zeolites are these porous materials, molecular sieves, basically.
Right.
And this system often gives excellent paraselectivity. Instead of a mix, you might get, say, 94% yield of just the para product, compared to maybe 1.8.1 para ortho with mixed acids.
Wow, that's a huge difference. How does that work?
The thinking is that the nitration happens inside the confined spaces of the zeolite pores. These channels can physically restrict access to the more crowded ortho position, favoring a more open parasite. It's shape-selective catalysis.
That's clever, using physical constraints at the molecular level.
It's brilliant. Leads to much cleaner products.
Okay, and another approach uses lanthanide salts, like ytterbium triflate.
YbO3SCF33. This catalyzes nitration using aqueous nitric acid, often in good yields. It's a gentler alternative to the really strong acids. The beauty here is that this catalytic procedure uses just a stoichiometric amount of nitric acid. No huge excess needed.
More efficient, less waste.
Exactly. And crucially, it avoids the excess strong acidity of conventional nitration, vital for sensitive substrates that might decompose. It's thought the lanthanide coordinates to the nitrate ion, activates it, helps generate or transfer the nitronium ion more gently. Cleaner reactions offer better yields for delicate molecules.
You can even make salts containing the nitronium ion itself, like NO2 plus BF4.
You can, yes. They're extremely powerful nitrating agents, but they require very careful handling, highly reactive.
Right.
And in a neat twist, nitrogen heterocycles like pyridine, they can form N-nitro salts with NO2BF4. And these N-nitro salts can then act as nitrating reagents themselves. It's called transfer nitration.
So you generate the reactive bit indirectly.
Exactly. Avoids handling the highly corrosive nitronium salts directly. Safer, more convenient sometimes, especially for sensitive starting materials.
Okay, and moving beyond typical electrophilic attack, ozone and nitrogen dioxide can also do nitration. A different mechanism.
Believed to be, yes. It likely involves the radicalization of the aromatic reactant, so an electron gets plucked off the ring first. Interestingly, compounds with oxygen substituents, like phenyl ethers, often show unusually high ortho-para ratios under these conditions, maybe 80% or so.
That's very specific. Why?
The idea is the nitronium ion might coordinate to the oxygen substituent first, then undergo an intramolecular transfer to the ortho position on the same molecule, internal delivery system.
Very elegant. Okay, maybe a couple of quick examples to really drive this home. How the reagent choice affects where the nitro group goes.
Sure. Think about aniline, the amino group. In acid, it gets protonated, becomes strongly electron withdrawal.
So it directs meta.
Directs meta, exactly. Deactivates the ring, too. Classic directing effect. Or nitrating dimethoxybenzene. You might find one methoxy group dominates, pushing the nitro group ortho to it, even with the other methoxy present. Subtle effects.
And the zeolite example.
Right. Nitrating toluene inside zeolite beta. Getting that 94% para product.
Yeah.
Huge difference from mixed acid. Means much cleaner product, less purification.
Right.
And that ozone NO2 radical pathway. Great for getting high ortho selectivity with some oxygenated rings, which is often hard otherwise. So chemists really pick their nitrating system strategically based on the target regioselectivity in the substrate.
Okay, next up, halogenation. Putting things like chlorine, bromine, fluorine onto the ring. Another super important step, right? Especially for pharmaceuticals, agrochemical.
Absolutely fundamental. Chlorine and bromine are quite reactive, but often need a push from Lewis acid catalysts to get good rates and control.
But fluorine, you said that's a different beast altogether.
Oh, yeah. Fluorine reacts very exothermically. High electronegativity, small size.
Yeah.
It's just incredibly reactive, so careful control of conditions is required. Seriously, handling elemental fluorine. It's tricky. Needs dilution, specialized equipment.
Sounds hazardous.
It can be. That's why developing milder fluorinating agents was such a big deal.
Yeah.
Iodine, on the other hand, is generally quite unreactive towards aromatic rings. These very activated rings are usually require special reagents or oxidants to make it happen.
Okay, so mechanistically for chlorine and bromine?
Chlorination is often acid catalyzed, and sometimes with complex kinetics. The proton helps break the Cl-Cl bond, makes it more electrophilic. Both chlorination and bromination are much faster in polar solvents, help stabilize charges in the transition state.
Right.
For actually doing the reactions preparatively, Lewis acids are key. Zinc chloride, ferric chloride for chlorination, metallic iron for bromination. It generates ferric bromide in situ. They help cleave the halogen bond by forming a polarized complex, making the halogen a much better electrophile.
Gotcha. But beyond the elements themselves, things like NBS and NCS are popular. N-bromosuccinimide, N-chlorosuccinimide.
Very popular, often preferred for convenience, easier handling, sometimes better selectivity than the elemental halogens. For instance, highly activated rings, like 1-hepta-2-camphor-trimethoxybenzene, brominate nicely with NBS at room temperature. That's wonderfully mild.
Yeah.
NCS and NBS can also halogenate moderately active rings in nonpolar solvents if you use acid catalysts like HCl or HClO4. Gives you more control, helps avoid ovum halogenation on reactive substrates.
Okay. And acyl hypohalites,
Yeah.
generated from mercury salts. Sounds aggressive.
They are very reactive. Trifluoroethyl hypobromite, for example. It can easily brominate even deactivated nitrobenzene.
Wow, that's tough to do usually.
It is. Shows the power of these highly active preformed electrophiles. Pushes the limits of EAS. Now, for very reactive things like anilines and phenols, they tend to just react everywhere. All activated positions get brominated.
Right, makes a mess.
Exactly. So you use more selective reagents, things like pyridinium, bromide, perbromide, or tetralkylammonium tribromides. They deliver the bromine more gently, allow for better control, maybe just monobromination. Critical for making specific compounds cleanly.
Okay, back to fluorine. Given its extreme reactivity, needing dilution and great care, how have chemists tamed it for practical use?
Well, they developed more manageable reagents. Acetyl hypofluorite, for instance, prepared in situ from fluorine and sodium acetate. It allows fluorination of activated aromatics with much greater selectivity, often shows a strong preference for orthofluorination with alkoxy or acetamido groups.
So, directing the untamable fluorine.
Exactly. Other notable safer regions include N-fluorobis, trifluoromethylsulfonureme, often called N-fluorotriflamide, and various N-fluoro derivatives of DIBCK, that bicyclic amine. These are often solids, easy to handle, controlled source of electrophilic fluorine. Transforms a dangerous reaction into a practical tool. And iodination typically needs iodine mixed with oxidants. Periodic acid, I2O5, silicon nitrate, something to generate a more reactive iodine species like I plus caro.
Right.
Mixtures of cuprous iodide and a cupric salt also work. For moderately reactive rings, iodine with silver or mercuric salts are effective to probably generate hypodides. Even deactivated rings can be iodinated using special reagents like bisaccharidy and iodonium salts with strong acids. So there are ways, even for iodine.
Let's look at some real-world examples again. The practical impact.
Absolutely. Think about a large-scale chlorination for a drug intermediate. Using NCS instead of chlorine gas allows a 75% yield on a 28-kilogram scale. Shows how crucial these selective reagents are for an industry. Or brominating an aniline in strong acid. You might expect just one bromine, but under vigorous conditions, all activated positions can get brominated. The acid might actually help successive brominations.
Huh. Counterintuitive.
It can be. And for fluorination, imagine taking an aryl triflate, usually unreactive, and converting it directly to an aryl fluoride in high yield using something like N-fluorotriflamide. These examples show the precision, scale, and versatility chemists now have for putting halogens onto rings.
Okay, now for a big one. Friedel-Crafts alkylation. A cornerstone method, right? For putting carbon chains, alkyl groups, onto aromatic rings, building up the carbon skeleton.
Absolutely foundational. The reactive electrophiles here, they can be either discrete carbocations, just a carbon atom with a positive charge, or polarized complexes with a leaving group, acting like a developing carbocation.
Okay.
You generate them using classic methods, alkyl halides with Lewis acids like aluminum chloride, or reacting alcohols or alkenes with strong acids like sulfuric or phosphoric acid. Depends on the alkyl group and the ring's reactivity.
Right. Now here's where it gets really interesting and often confusing for students. I remember this. Because carbocations are involved, you can get rearrangements.
That's the crux of it, a major complication. The carbocation intermediate itself is prone to rearranging into a more stable form before it even attacks the ring.
So you aim for a straight chain, you might get branched.
Precisely. Like you start with N-propyl chloride, hoping for an N-propyl group. You often end up introducing an isopropyl group instead.
Why?
The initially formed primary N-propyl carbocation does a quick hydride shift to form the more stable secondary isopropyl carbocation. Happens super fast. Rearrangement can even happen after the initial alkylation, especially with strong catalysts like LCl3, leading to the most thermodynamically stable product. Alkyl groups can even migrate around the ring, usually to minimize steric hindrance, makes precise control tricky. So choosing the right Lewis acid catalyst is crucial to try and minimize these rearrangements. But there are other limitations too. Friedel-Crafts alkylation doesn't work well if the aromatic ring already has electron withdrawing groups.
Because they deactivate the ring.
Right. Makes it too sluggish for the electrophilic attack. Also a big practical challenge. Each alkyl group you add activates the ring further. Alkyl groups donate electrons.
Oh, so you get polyalkylation. Multiple additions.
Exactly. Hard to stop at just one. To minimize this, you often use a huge excess of the aromatic reactant. Flood the system. Try to give the electrophile more chance of finding an unreacted ring.
Okay. So besides alkyl halides, what else can generate these carbocations? You mentioned alcohols and alkenes.
Yep. Alcohols react in strong acids like sulfuric or with Lewis acids like BF3.
Yeah.
The acid protonates the alcohol, makes water a good leaving group, generates the carbocation. Alkenes work too with picocorbatic or Lewis acids. The acid protonates the double bond to form the carbocation. And for more stabilized carbocations like allylic or benzylic ones from alcohols, you can use milder catalysts like scandium triflate. That's actually been used in synthesizing vitamin E, alpha-tocopherol. Shows its utility in complex synthesis.
So how does this apply to making more complex structures, like building new rings? Intramolecular Friedel-Crafts sounds powerful.
It is incredibly important for building polycyclic frameworks. But there's a general rule, or maybe a strong tendency. It's somewhat easier to form 6-membered rings than 5-membered rings in these cyclizations.
Why is that?
For example, 4-phenyl-1-butanol might give a decent yield of a 6-membered ring. But try to make a 5-membered ring from 3-phenyl-1-propanol. It often just dehydrates to an alkene instead. The difficulty with 5-membered rings, it's thought to be a mix of steric and electronic factors. Strain from putting sp2 carbons in a small ring, difficulty aligning the carbocation's p orbital with the pi system, plus if the carbocation can rearrange via a hydride or alkyl shift, it usually will in preference to closing that tricky 5-membered ring. Delicate balance. Give a concrete example. Imagine cyclizing a complex alcohol. You might form a new ring junction with a methyl group, but get maybe a 3.1 mixture of alpha versus beta isomers, reflects slight energy differences in the transition states.
Right.
Or take in an enantiomerically pure alcohol starting material. After an intramolecular Friedel-Crafts, the product might be nearly racemic, a 50.50 mix of mirror images.
Why lose the chirality?
Because you form that planar carbocation intermediate, the ring can attack it from either face equally easily, wipes out the original stereochemistry, emphasizes how the intermediate dictates the outcome.
Okay, moving from alkyl to acyl groups, that's introducing a carbonyl, CO, Friedel-Crafts acylation, typically an acyl halide and a Lewis acid again.
That's the standard approach, yes.
Yeah.
Common Lewis acids. LCl3, SBF5, BF3. Bismuth-3 triflate is also noted as very active, often allowing milder conditions. Acid anhydrides work too. For example, hafnium triflate with lithium perchlorate can catalyze acylation using acetic anhydride. And mixed anhydrides, especially with trifluoroacetic acid, are particularly reactive, really potent acylating agents for tough cases. The reactive intermediate is usually a dissociated acylium ion that's RC triple bond O+, resonance stabilized. Or it could be a complex of the acid chloride and Lewis acid. Recent studies suggest, interestingly, that with benzene or slightly deactivated rings, the protonated acylium ion might actually be the kinetically dominant electrophile, the one that reacts fastest. Regioselectivity.
Yeah.
It could be sensitive to solvent and stuff, but generally paratach dominates for alkyl benzenes. Sterics usually win out.
Less crowded.
Less crowded. But interestingly, ortho attack can increase significantly if the acylium ion is highly electrophilic. Can get up to 50% ortho sometimes. So it's a balance between sterics and electronics.
Right. Now here's the big advantage, the game changer compared to alkylation. No rearrangements of the acyl group, right? And no polyacylation.
That's absolutely right. And it's a huge strategic plus for synthesis. The psyllium ion is resonance stabilized, much less prone to rearranging like simple alkyl carbocations.
Okay.
And crucially, the first acyl group introduced deactivates the ring to further attack. It's electron withdrawing, so naturally prevents multiple acylations. You reliably get just one.
That's fantastic control.
It is. That's why chemists often prefer a two-step route for primary alkyl groups. First, acylate the ring, then reduce the carbonyl down to an alkyl group.
Yeah. Bypasses all the problems of direct alkylation.
Exactly. Avoids rearrangement, avoids polyalkylation. Much cleaner, more predictable.
Smart. Okay, intramolecular acylations, making fused rings. Common.
Very common, very useful. The usual conditions work: acyl halide, Lewis acid. A classic alternative, especially if you start with a carboxylic acid, is dissolving it in polyphosphoric acid, PPA, and heating. Probably forms a mixed anhydride in situ.
Okay.
Other options: polyphosphate ester, chloroform soluble, milder, trimethylsilly polyphosphate. Neat methane sulfonic acid works too. There's a classical sequence for fusing a six-membered ring. Start with succinic anhydride, do an intermolecular acylation, then reduce the ketone.
Why reduce?
To reactivate the ring, because the first acyl group deactivated it. After a reduction, then you do the intramolecular acylation to close the second ring. Clever sequence. And a special case is the Fry's rearrangement that's converting an ester of a phenol into an orthoacyl phenol, or sometimes para, catalyzed by a Lewis acid.
Ah, rearranging an existing group.
Exactly. For example, a phenol ester with BF3 might give the orthoacylated product in 92% yield. Lanthanide triflates are also good catalysts, very useful for making orthoacylated phenols directly.
Let's see some examples again. Scheme 11.4.
Right. There's a great example of using mixed trifluoroacetic anhydride for a kilogram scale acylation, making a starting material for the anti-cancer drug tamoxifen. Shows the industrial relevance.
Whoa.
Another uses bismuth triflate as the Lewis acid effectively. And then there are typical examples of intermolecular acylations forming new fused rings. Really showcases the power of acylation for controlled CC bond formation and building complex architectures.
Okay, beyond the classic Friedel-Crafts, there are important variations. Chloromethylation. Adding a CH2Cl group.
Yes, introduces a chloromethyl substituent. You react the aromatic with formaldehyde in concentrated HCl, usually with zinc chloride. The electrophile is likely the chloromethyllium ion, CH2Cl plus Cl. Works well with benzene, activated rings. Or you can use chloromethyl ethers with SnCl4.
And that CH2Cl group is useful because
chlorine is easily displaced. So it's a great handle for further transformations, make amines, alcohols, nitriles, aldehydes. Very versatile intermediate.
Right. And it's fascinating that even tiny molecules like carbon monoxide, hydrogen cyanonitrils, they can react with aromatics to add formal DABA-CO or acyl groups.
It is fascinating. Requires strong acids or Friedel-Crafts catalysts. The active electrophiles are believed to be dications from deiprotonation of CO, HCN, or the nitrile.
Dications, two positive charges.
Yep, like HC plus OCO attacking the ring for formulation with CO, or RC plus NH2 from a nitrile. The initial adducts were then hydrolyzed, just add water to get the aldehyde or ketone. Dichloromethyl ethers can also be formal group precursors. The dichloromethyl group gets hydrolyzed to an aldehyde after alkylation, but a crucial warning. Bis-chloromethyl ether, potent carcinogen, needs extreme care, safety first. Another widely used method for formal and acyl groups is the Vilsmeier-Hack reaction.
Ah, yes, Vilsmeier-Hack.
Here, N and dialkylamides react with POCE3 or oxalyl chloride, forms a chlorominium ion, RCCl-NCH32, plus A. That's the active electrophile. And it's reactive enough that it can often react without an added Lewis acid, but usually only with highly activated aromatic rings. Great for making aldehydes or ketones from electron-rich aromatics. So looking at examples, formulation using CO might give yields around 46–51%. Using HCN and ZN, CN2, could push that up to 75–81%.
Okay.
And Vilsmeier-Hack, applying it to strongly activated rings like indoles or pyrroles, reliably gives the aldehyde excellent yields. Shows its power for those electron-rich systems where other electrophiles might struggle. All neat ways to add small carbon bits.
Okay, aromatics can also react with metal salts. Mercuration. Putting mercury onto the ring. Seems odd, but you said it's useful.
It is, as an intermediate step. Mercuric acetate or trifluoroacetate are common. The reaction shows typical EAS substituent effects. But what's fascinating, mercuration is one of the few EAS reactions where proton loss from the sigma complex is the rate-determining step.
The slow step is losing the proton, not the initial attack.
Exactly. We know this from a significant isotope effect. Replacing H with D slows the reaction down by about 6 times, shows the initial attack is reversible. Breaking that CH bond is the bottleneck.
Okay, so why make these aryl mercury compounds?
Their synthetic utility lies in what you do next. The CHG bond reacts with various electrophiles, useful for making nitroso compounds with nitrous silyl chloride. And they're valuable in some palladium-catalyzed reactions too, as aryl group donors. Thallium-30 is another option, especially thallium-serine trifluoroacetate, highly reactive electrophilic metallating agent. Lots of synthetic schemes use these aryl thallium intermediates. They're very versatile. You can convert them to chlorides or bromides with copper halides, to iodides with potassium iodide, fluorides via KF, then BF3. Even procedures for nitriles and phenols exist, like a chemical switchboard.
So what's the big advantage of using thallium? Sounds like it offers unique control.
It absolutely can. Aryl thallium intermediates are incredibly useful for directing substitution to specific positions if you can control where the thallium goes initially. 2 key controls: chelation and thermal equilibration.
Butyllation.
Right. Oxygen-containing groups, like methoxy, often direct thalation to the ortho position. The thallium coordinates the oxygen, then attacks next door. Very specific ortho substitution.
Nice. And thermal equilibration.
Interestingly, for alkyl denzenes, the thermodynamically favored position is usually meta. So if you heat the aryl thallium derivatives, they can rearrange to favor the meta isomer. Offers complementary regioselectivity to many other EAS reactions which favor orthopara. Powerful tool for accessing meta-substituted products. But, and this is critical, we must emphasize, both mercury and thallium compounds are very toxic.
Right. Heavy metals.
Very toxic. Special care, rigorous safety protocols, robust precautions are absolutely necessary when handling them. Safety is paramount.
Okay, we've spent a lot of time on electrophilic attack, electron-loving species hitting the electron-rich ring, but aromatic compounds can also undergo substitution by nucleophilic reagents, where an electron-rich species attacks an electron-poor ring. Kind of the opposite situation.
Exactly. It's a fundamental paradigm shift.
Yeah.
But unlike nucleophilic substitution on saturated carbons, which is often that single-step SN2 process.
Right, the backside attack.
Aromatic nucleophilic substitution does not occur by a single-step mechanism directly displacing a group. That pathway is just blocked geometrically and electronically on an sp2 carbon in a ring.
So how does it happen?
Well, there are different mechanisms. One is the addition elimination mechanism, SNAR. Nucleophile adds first, forms that Meisenheimer complex intermediate, then the leaving group leaves.
Okay.
Another is elimination addition, which involves that wild intermediate benzyne.
Right.
And then, as we touched on, metal-catalyzed processes have become incredibly important, revolutionizing this area. We'll get to those separately. Okay, let's revisit aryl diazonium ions. We said they're versatile intermediates. How do we make them? Typically react and analyze an amino group on a benzene ring with nitrous acid, usually generate the nitrous acid in situ from a nitrate salt and acid. Crucially, unlike their aliphatic cousins, which fall apart instantly, aryl diazonium ions are stable enough to hang around in solution at room temp, or even be isolated as salts, especially with non-nucleophilic anions like tetrafluoroborate.
Why are they more stable?
Delocalization involving the aromatic ring helps stabilize them. Their formation involves the nitrosonium ion, NO plus ANO, adding to the amino group, then loss of water. In base, they can convert to other species, like diazoate anions, important for some radical chemistry, can also make them in organic solvents using alkyl nitrites.
Okay, so what makes them such a big deal for substitution? You mentioned the leaving group.
Their huge synthetic utility comes from the excellence of N2, molecular nitrogen, as a leaving group.
Yeah.
Nitrogen gas is incredibly stable.
Right, wants to form.
Exactly. So its departure provides a massive thermodynamic driving force, makes the reaction go. And there are several ways substitution can happen from these intermediates. One mechanism is unimolecular thermal decomposition. Just heat the diazonium ion, it falls apart, loses N2, forms a highly unstable aryl cation.
Positive charge on the ring carbon.
Yep. Highly unstable, highly unselective. Reacts instantly with whatever's around solvent, anions. Seen in hydrolysis to phenols, where water attacks the lubrication. A second way is adduct formation and collapse. The diazonium ion forms a temporary bond, an adduct, with a nucleophile. Then that adduct collapses, kicks out N2, forms the product. Happens with a Zide ion to form aryl azides, for example. And a third very important mechanism, especially with copper catalysts, involves redox processes. Often starts with oxidative addition of the diazonium ion to Q, forms a transient Q intermediate. Then halide transfer, or reductive elimination, gives the product and regenerates the catalyst. This is the basis of the famous Sandmeyer reaction, hashtag reductive de-diazonization, replacing NO2 or metaj NH2 with NOH.
Okay, sometimes you use a nitro or amino group to direct a reaction, but then you want to get rid of it. Just replace it with hydrogen. How do you do that using diazonium chemistry?
That's called reductive de-diazonization. The best reagents are hypophosphorus acid, H3PO2, or NaBH4, sodium borohydride. Hypophosphorus acid works much better with catalysis by cuprous oxide. The mechanism likely involves a one-electron reduction of the diazonium ion to form a phenyl radical.
Ah, radical intermediate.
Yep, that radical then grabs a hydrogen atom from the hypophosphorus acid. Clean way to swap a NaCH2 for a beige. Another method is in situ diazotization with an alkyl nitrite in DMF solvent. Here, the DMF itself acts as the H atom donor in a chain reaction, often catalyzed by iron sulfate. Very useful for defunctionalizing that position. Hashtag phenols from diazonium ion intermediates. Replacement by H. You can convert aryl diazonium ions to phenols just by heating them in water. Probably forms the phenylcation which water attacks.
Okay, simple enough.
But a more versatile and efficient method uses a redox mechanism, initiated by cuprous oxide with C-Chi, converts the diazonium ion to an aryl radical, which is captured by Q to I, then converted to phenol via reductive elimination. This copper way is very fast, gives good yields. Powerful way to put an azo H group on the ring. Hashtag aryl halides from diazonium ion intermediates. Replacement by diacetyl by IF.
Okay, for aryl chlorides and bromides, the Sandmeyer reaction is the classic, right? Using copper salts.
Yes, absolutely key. Uses the appropriate Qi salt, cuprous chloride or bromide. Classic conditions. Add the diazonium salt to a hot acidic solution of the cuprous halide. Mechanism involves oxidative addition to Qi, then halide transfer from a Q intermediate, kicks out N2. Reliable.
Are there alternatives?
Sure. Can get good yields of chlorides from isolated diazonium tetrafluorohydrates using iron chloride mixtures. Or, for convenience, in situ diazotization with alkyl nitrites and Q2 halides and acetonitrile. Avoids isolating the diazonium salt, which can be nice. You can also make halides via aryl-free radicals, an alternative to Sandmeyer, maybe for trickier cases. In basic solutions, diazonium ions can form radicals via diazooxides. Can do this efficiently using diazonium tetrafluorohydrates with crown ethers or phase transfer catalysts. If you do this in a solvent that can donate a halogen atom, like bromotrichloromethanes for bromine, CCl4 for chlorine, methyl iodide for iodine. The aryl radical just abstracts the halogen. This radical method was used for a tough chlorodeamination in the vancomycin synthesis. Shows its power.
Right, and for fluorine, that tricky halogen, there's a Scheinman reaction.
Yep. Involves isolating aryl diazonium tetrafluorohydrates, then heating them. They decompose to give aryl fluorides, believed to involve an arylcation grabbing fluoride from the BF4 anion. Hexafluorophosphate salts work similarly. Reliable route to aryl fluorides, though needs isolation. Milder conditions are being developed too, and iodides are easy. Just react the diazonium ion with iodide salts like Ki, high yields, initiated by reduction of the diazonium ion by iodide, forms an aryl radical which then abstracts iodine. Radical chain mechanism confirmed by cyclization experiments, hashtag introduction of other nucleophiles, cyanoizidothiolates. Beyond halogens and OH cyano, and nido, matching N3 groups, are also readily introduced via diazonium ions. Cyanide usually uses a copper-catalyzed reaction, like Sandmeyer. For azides, reaction with azide ion gives an adduct that smoothly decomposes to N2 and the aryl azide. Very clean. Aryl thiolates also react to give diaryl sulfides, probably via a radical chain similar to the iodide reaction, shows the breadth of nucleophiles you can use. So looking at scheme 11.6 in the book, you see examples of all this. Reductive de-diazonizations with hypophosphorus acid. Classic Sandmeyer reactions for Cl and Br. That tricky chlorodeamination on vancomycin using the radical atom transfer method. And clean introductions of cyano and azido groups. Really highlights the practical power of diazonium chemistry.
Okay, so far mostly swapping atoms. But can diazonium ions help build new carbon bonds? That's the holy grail, often in synthesis.
Absolutely. That brings us to the Meerwein arylation reaction. It's a copper-catalyzed reaction of diazonium ions with conjugated alkenes. Result, arylation of the alkene. I'm attaching an aryl group directly to a CC double bond.
How does that work?
Initiated by reduction of the diazonium ion by Q, forms an aryl radical. Radical adds to the alkene, creates a new beta-aryl radical. Final step involves ligand transfer from copper, or sometimes oxidation deprotonation gives a styrene. Powerful way to make CC bonds. It generally gives better yield with dienes, styrenes, or alkenes that have electron-withdrawing groups, EWGs, attached, like nitriles or esters.
Why?
Because those groups help stabilize the intermediate radical, makes the alkene better at trapping the aryl radical. Standard conditions use aqueous diazonium ions, but in situ diazotization with T-butyl nitrite and QCl2 is often effective and convenient. There's also a reloaded method using Ti3, titanium-3, as the reductant. With beta, gamma unsaturated ketones or aldehydes, this leads to alpha arylation and forms a saturated ketone or aldehyde.
Saturate.
Early steps are similar aryl radical adds to the alkane, but instead of oxidation, the resulting radical gets reduced by Ti3 to an anion, which then gets protonated, gives the saturated product. Complementary outcome. So looking at examples in scheme 11.7, you see typical Meerwein conditions coupling an aryl radical to an alkene like acrylonitrile, making an arylated nitrile. Or using the Ti3 reductive conditions with an unsaturated ketone, you get an alpha arylated saturated ketone. Shows the control you can have over the final product structure. Powerful ways to build carbon skeletons.
Okay, let's circle back to direct nucleophilic substitution on aromatic rings. The addition-elimination mechanism, Essner. You mentioned that Meisenheimer complex intermediate. What's really happening there?
Fundamentally, it's addition of a nucleophile to the aromatic ring, usually at a carbon that has a leaving group. This forms that Meisenheimer complex intermediate.
Which is anionic, resonance stabilized.
Right, negative charge spread around the ring. Then in the second step, there's elimination of a substituent. The leaving group departs. The energetic hurdle is forming that intermediate because you temporarily disrupt the aromaticity. And that addition step is greatly facilitated by strongly electron-attracting substituents, EWGs, on the ring, especially nitro groups. They make nitroaromatics excellent reactants for SNOR.
Why?
They stabilize the negative charge of the Meisenheimer complex by pulling electron density toward themselves, lowers the energy barrier for the nucleophile to add. Other activating EWGs. Cyano, acetyl, trifluoromethyl, ylides are common leaving groups, but alkoxy, cyano, nitro, sulfonyl groups can also leave.
Okay, and here's that counterintuitive point again. Fluoride is often a better leaving group than other halogens in nucleophilic aromatic substitution. Why? It's such a strong bond.
Exactly. It trips everyone up initially if they're thinking SN2.
Wrong.
But in SNR, remember, bond breaking isn't the slow step. It's the addition of the nucleophile.
Forming the Meisenheimer complex.
Right. And fluorine, being so highly electronegative, it favors the addition step more than other halogens. It powerfully withdraws electron density, stabilizing the negative charge that develops in that intermediate.
Ah, so it helps the hard step happen more easily?
Precisely. Lowers the activation energy for addition. So even though the CF bond is strong, that electronegativity effect wins out in this mechanism. A beautiful example of how mechanism dictates reactivity trends. One limitation, though. Aromatic nitro compounds, while great for SNR, sometimes react with carbanions via electron transfer processes, can complicate direct C arylation. But SNR is very important in heteroaromatic nitrogen compounds, like pyridines.
Because the nitrogen atom pulls electrons.
Exactly. Makes the ring electron-deficient, reactive at C2 and C4. Nitrogen helps stabilize the addition intermediate, crucial for functionalizing things like pyrimidines in medicinal chemistry. There's a fascinating variation. Vicarious nucleophilic aromatic substitution, VNISS. Here, the leaving group is actually part of the entering nucleophile itself.
Wow, self-contained.
Clever, right? Requires a strong EWG like nitro on the ring, but the ring doesn't need a pre-installed halide leaving group. Works via addition intermediates. For example, the attack nucleophile might have both a cyanide group and a hydrogen or halogen on the same carbon, and the H or halogen acts as the leaving group after attack. Expands the scope significantly. So practical examples from scheme 11.8. Reacting 2-4 dinitro-nitrochlorobenzene, highly activated, with an amine. Displaces the chlorine cleanly, often needs heat, rather vigorous conditions, but reliable. Or an interesting case where an acetyl group activates the ring. An aromatic fluoroketone might react with dimethylene in high yield, while the chloro and bromo versions are much slower. Again, reinforces fluoride's special role in SNR due to its electronegativity stabilizing that intermediate. Shows SNR is good for CN and CC bonds, especially on electron-poor rings.
Okay, the next mechanism involves this highly unstable transient intermediate called dihydrobenzene, or more commonly benzene, sounds exotic, like benzene with an extra superstrained triple bond.
That's a perfect description. Think of a triple bond forced into that 6-membered ring, highly strained, incredibly reactive.
Right.
And the unique feature of this mechanism, the incoming nucleophile, does not necessarily become bound to the carbon to which the leaving group was originally attached,
Why not?
because that benzyne intermediate is symmetrical across the triple bond. The nucleophile can add to either end, so you often get mixtures of products if the original ring was substituted. Regioselectivity can be an issue. What favors this mechanism? Electronic effects that help remove a proton from the ring, usually by a strong base. Relative reactivity also depends on the halide leaving group. With strong bases like KNH2 and ammonia, the order is BRICLF.
So bond breaking matters more there.
Seems like it. Reflects a balance. Polarity favors proton removal near F, but ease of CX bond breaking, IBRCLF, outweighs it. But switch to organolithium reagents in ether, the order flips, FClBRI.
Why the change?
Suggests that under those conditions, the acidity of the ring hydrogen, higher near electronegative F, becomes the dominant factor controlling benzyne formation. Subtle interplay.
Given how reactive benzyne is, like a chemical ghost, how do chemists generate it controllably for synthesis?
Great question. There are better ways than just strong base on halobenzenes. Probably the most useful method is diazotizing orthoamidobenzoic acids.
Anthranilic acid derivative.
Right. After diazotization, loss of N2 and CO2 cleanly generates benzyne. Advantage: you can generate it in the presence of whatever you want it to react with. In situ trapping.
Nice. Other ways.
Oxidation of 1-aminobenzotriazole works well, loses 2 N2 molecules under mild conditions. Decomposition of benzothiadiazole 1,1-dioxide also works, loses N2 and SO2. Elegant ways to make this fleeting species, and once you make it, benzyne is extremely reactive. Addition to nucleophiles like ammonia, alcohols, or conjugate bases happens very rapidly. Nucleophile attacks, then protonation gives the product. Selectivity can be moderate with substituted benzynes, often get mixtures.
What if there's nothing else around for it to react with?
It dimerizes to biphenylene, forms a four-membered ring fused to 2 benzenes. But it's also a very reactive dienophile. Loves to do Diels-Alder reactions.
4+2 cycloadditions.
Exactly. Reacts with dienes like furan. Those adducts can then be converted to complex polycyclics. Reacts with cyclopentadienes, losing CO to form a new aromatic ring, with pyrones losing CO2. Even does 2+2 cycloadditions and N reactions with simple alkenes. Powerful for building complex structures. Scheme 11.9 shows some clever uses. A Diels-Alder trapping benzyne with furan to make strained polycycles, generating benzyne from O-bromofluorobenzene with magnesium, reacting it with anthracene.
Cool.
Even an intramolecular trapping of benzyne by a nitrile-stabilized carbanion in the same molecule forms a new ring. And a Diels-Alder with a pyrone where the adduct loses CO2 to make a new aromatic ring shows that despite being fleeting, benzyne is a potent synthetic tool.
Okay, now we move into arguably the most exciting transformative area today.
Transition metal catalysis. We said direct nucleophilic substitution on unactivated aryl halides is really tough. So what's the revolutionary solution? How do we get those nucleophiles on cleanly and efficiently?
This is exactly where transition metal catalysis shines. It opens up entirely new reactivity. For a long time, we've known copper metal or salts can catalyze these reactions.
Right.
But often needed harsh, high temperatures. More recently, palladium catalysis has truly revolutionized the field. Milder conditions, incredible versatility, broad applicability, unlocked a vast library of new synthetic routes. Historically, copper catalysis was used for things like making aryl nitriles from aryl bromides with CICN, often needed high temperatures like over 200 degrees C in DMF.
General mechanism involves oxidative addition of the aryl halide to QI. Metal inserts into the CX bond. Then the resulting aryl copper intermediate collapses via ligand transfer or reductive elimination, forming the product and regenerating the catalyst. Many nucleophiles work. Carboxylates, alkoxides, amines, phthalimide anions, thiolates, acylides. Most older reactions used high temps, heterogeneous conditions with copper powder or bronze, but using soluble QI salts, especially copper I triflate, allows homogeneous reactions under much milder conditions.
Right.
For instance, coupling aryl halides and phenolates to make diaryl ethers. Much better using CsCO3 base in refluxing toluene yields around 80%. Adding naphthoic acid can accelerate some reactions, maybe via mixed anionic cuprates.
So what was the secret to making these copper reactions milder? Just soluble salts or?
More than that. A key breakthrough is finding beadentate ligands. Ligands that grab the copper in 2 places form a stable chelate ring.
Ligands again?
Yes. For instance, QI iodide with a chelating diamine like trans-N, dimethylcyclohexane 1-yarkyl-2-diamine. Excellent catalyst for amidating aryl bromides and iodides, even hindered ones. Works on a wide range of aryl halides, EWGs or ERGs, cyclic or acyclic amines. even promotes iodide-bromide exchange.
Wow.
Another useful ligand, the N-diethylamide of salicylic acid, allows amination by primary alkylenes. Ki iodide with 11,10-phenanthroline catalyzes substitution by alcohols. These ligands stabilize the copper, make it more efficient, allow milder conditions. The general reactivity order, IBrClOSO2R, sulfonates, totally consistent with oxidative addition being key. Easier CX bond breaking reacts faster. The exact active catalyst species is still researched. Maybe anionic cuprates are involved sometimes. Still learning. So practical examples from Scheme 11.2, Part A, arylating imidazole with an aryl bromide, 96% yield using copper triflate with ligands. Amination by a primary mean, 95% yield with a specific copper diamine system. Even older methods using copper powder for pharma intermediates might give decent yields, like 61%, but these ligand systems offer huge advantages in efficiency, selectivity, and mildness.
Okay, if copper is the seasoned pro, palladium is the undisputed superstar now in cross-coupling and aromatic substitution. It really transformed synthesis, right? Led to a Nobel Prize?
Absolutely. Palladium catalysts, especially combined with specific phosphine ligands, are incredibly effective, like converting aryl iodides to nitriles at mild conditions with PBH3 or 4 catalysts, maybe 89% yield. A huge amount of research focused on finding catalysts for CO and CN bond formation, critical for so many drugs and materials. And the key fundamentally is the ligands. Optimized catalysis with trigrylphosphines, bisphosphines like BINAP, DPPF, phosphines with extra-chelating groups. Fascinatingly, some of the most effective catalysts use highly hindered trialkylphosphine.
Bulky phosphines, like tritibutylphosphine.
Exactly, or tricyclohexylphosphine. They provide this protective, flexible pocket around the palladium, helps stabilize it, promotes key steps like reductive elimination, leads to faster reactions, higher yields. Also, 2-biphenylphosphines show excellent activity. Even stable palidocycles palladium in a ring are active, robust, easy-to-handle catalysts.
And these work on more than just iodides and bromides.
Oh, yes. They allow substitution not just of bromides and iodides, but also chlorides, triflates, even nonaflates, non-fluorobutane sulfonates, usually in much less reactive leaving groups.
So you can use cheaper starting materials like chlorides.
Exactly. Broadens the scope dramatically, permits substitution on electron-poor and electron-rich rings by a huge variety of nitrogen nucleophiles, amines, heterocycles, indispensable now for CN, CO, even CS bonds. The reactions generally follow a catalytic cycle. PD0 and PDII intermediates. Starts with the oxidative addition of the aryl halide to PD0. Parallax bond breaks, both bits add to PD.
Increases oxidation state.
Right. Then ligand exchange, the nucleophile comes in. Then reductive elimination, the new CN or CO bond forms, kicks off the product, regenerates the PD0 catalyst. Cycle repeats.
Sounds smooth, but complex underneath.
Very. Kinetics show details vary. Sometimes an amine adds before oxidative addition. Reductive elimination often needs deprotonation first. Might be concurrent mechanisms depending on the base. Activation often involves a diphosphine ligand dissociating to monophosphine, explains why hindered ones work well. Deprotonation of the amine is crucial. If you start with PD-ABRI, it needs reduction to PD-ARO, often by the amine itself.
So the ligand and base choice, it's not just for speed, but affects the exact pathway and catalyst lifetime.
Exactly. These palladium species can decompose, deposit palladium, metal turns black, catalyst dies. Ligands and bases are critical for catalyst longevity as well as activity. They stabilize the active species, keep the cycle turning over efficiently, prevent catalyst death. Most applications came from tons of empirical screening. Optimizing for specific reactions, like aryl chlorides are less reactive, but specific catalysts, like that palidocycle, work well for their amination, 94% yield sometimes. Can even use palladium for non-basic N-heterocycles like indoles. Aryl sulfonates are tough, but certain catalysts with hindered biphenylphosphines work. Also successful for arylating amides, carbamates. Hindered binaphyl ligands are good for alcohols. Palladium acetate with xanthos ligand works for amides, ureas, oxazolidinone, sulfonamides. Just immense scope. So looking at Scheme 11.10, Parts B and C, examples of aminating aryl chlorides with high yields using different PD-phosphine catalysts. A large scale, 15 kilogram amination using a protected amine, reactions with tricky aryl triflates. And successful arylations of alkoxides and phenoxides, often needing those highly hindered phosphine ligands to get great yields, like 92% for tert-butoxy substitution. This paints a picture of the precision and power palladium brings.
Okay, finally, let's explore reactions involving free radicals, an atom or group with an unpaired electron. Highly reactive. You said aromatic rings are moderately reactive to radical addition, offering some unconventional paths.
They do. One key application is synthesizing biaryls, two aryl groups joined by a CC bond. But there are limits. Radical substitutions are only moderately sensitive to substituent directing effects.
Meaning you get mixtures if the ring is substituted. Low regioselectivity.
Often, yes. Makes it hard to control exactly where the bond forms. So practical utility is often limited to symmetrical reactants, like benzene coupling with itself, where position doesn't matter. Best sources of aryl radicals for this: aryl diazonium ions again, or N-nitrosoacetanides. Diazonium ions in base form diazooxides, which decompose to aryl radicals, can improve yields using phase transfer catalysts with solid diazonium salts and excess aromatic reactant. N-nitrosoacetanides rearrange to diazonium acetates, then give radicals. In situ diazotization procedures exist too, so examples from scheme 11.100, a classical biaryl synthesis, using crown ethers to improve yields. Studies show substituted aromatics like toluene might give a bit more ortho-substitution than random, so some directive effect, but not great. Decomposing N-nitrosoamides in situ also gives decent yields of biaryls, valuable routes for symmetrical biaryls.
Okay, last one. The SRN1 mechanism. Aromatic nucleophilic substitution via a radical chain. You said it has a really distinctive feature, electron transfer.
Indeed. The defining characteristic is an electron transfer between the nucleophile and the aryl halide. This kicks off a chain process. It's not just attack, it's electron movement first. A potential advantage. SRN1 is not particularly sensitive to the nature of other aromatic ring substituents. Works on a broader range than maybe SNAR sometimes. EWGs help the initial electron transfer, but it's robust. For instance, chloropyridines, chloroquinolines, often tough substrates, are excellent reactants for SRN1, great for functionalizing heterocycles, and a wide variety of nucleophiles work. Ketone enolates, ester enolates, amide enolates, dianions, pentadienyl carbanions, also phenolates, phosphidanions, phosphides, thiolates. Broad scope.
Initiated by light, often.
Frequently initiated by light, yeah. Promotes that crucial initial electron transfer. But like any radical chain, it's sensitive to inhibitors that can intercept the propagating radicals. Need clean conditions. Scheme 11.12 shows strong examples. Arylating ketone enolates in high yield, often needing light. A unique case with a dianion reacting, 79% yield. A convenient prep for aryl using diphosphide anion, 84% yield. And applying SRN1 to a chloropyridine, 65% yield, proves its utility for heterocycles, underscores the unconventional but powerful nature of electron transfer and aromatic substitution. Hashtag tag outro. So wrapping this up, we've taken quite a deep dive into the fascinating world of aromatic substitution reactions. From those historical electrophilic additions putting groups onto rings,
Yeah, the class.
to the more nuanced nucleophilic and radical pathways, and especially this modern era of transition metal catalysis.
Yeah.
You can really see the incredible toolkit chemists have developed to precisely modify these stable aromatic systems.
Absolutely. From making something relatively simple like aspirin in a lab, all the way to synthesizing incredibly complex drug candidates like tamoxifen or the antibiotic vancomycin. These reactions are just foundational. We've seen how a tiny change in a catalyst or a deeper understanding of a fleeting intermediate like a benzyne or a carbocation can completely change the outcome and efficiency. It really is where chemical synthesis becomes both an art and a science.
That's beautifully put.
A blend of precise knowledge and creative problem solving.
And connecting it to the bigger picture. It just highlights how fundamental understanding of reaction mechanisms combined with innovative catalyst design constantly expands what's possible. This field isn't static, it's always evolving, building on past knowledge to create the materials and medicines of the future, pushing the boundaries of molecular construction.
And this deep dive, well, it's just the beginning, really. We hope this exploration has given you a fresh perspective, maybe sparked a new curiosity for the elegance and, yeah, the power of organic chemistry. Keep digging, keep exploring, keep asking why.
Definitely.
Thank you so much for joining us for this deep dive. Until next time, stay curious.